in this video we're going to be doing vector force table. The objective of this experiment is to study vectors using equilibrium of forces. The idea is that by using forces we can balance out a system so that it's in equilibrium and then use vector arithmetic to solve that problem. By doing so we can study the behavior of vectors, and here you can see what that force table looks like. Right? So we have that the vector force table starts at 0 right over there, right? And goes around, make all the way back to 0 to make a total of 360 degrees. Right? So with those markers that you see there, you can determine the angle in a circular system, and with that you set up a system of pulleys. So you have a system of pulleys, and you can see over here, right, there's 3. And if we take a different look at that, you can see what the pulley system looks like in here. Right? So you have the vector force table. The ring here is the same ring that you see over here, right? We're taking a look from this perspective. So if you look over here, each pulley is attached by a wire to the ring, and then that wire is connected to a hanger, and that hanger has a certain amount of masses hanging from them. So if you look at the experiment tells you that for vector A, right over here, you need a total of 27 grams. And you have to place it at an angle of 63 degrees. So when you're doing this experiment, thankfully this one's already set up over here, right? If you look at this line over here, this indentation right here, you see that it's marking that over there, which is 63 degrees. Right? So you set it up so those indentations are where they're supposed to be. In the first case for A, it tells you 27 grams at an angle of 63 degrees. So, like you see over here. In this one, you can see the indentation. You can see the indentation right over here, right? And it's marking this line over here, which is 151, 152, 153, 154. Right? So, as the handout says, we position the second pulley at an angle of 154, and then we position 41 grams in the hanger. So the system will look like this with the corresponding hangers hanging from the pulleys. Right? So this be your C, this over here is your B, and then out of frame is A. So the idea is that if we do a system like this, we can make the system be in equilibrium. So if you look over here, this ring is not touching this portion over here, which indicates that there is a corresponding balance of forces between A, B, and C, and the system is staying still. That's what it means to be in equilibrium. That it has a 0 acceleration, meaning that it's standing still or moving at a constant velocity. Since you can, well, it's a picture so you can't see, but in the video you can see that when it reaches equilibrium, the ring stays completely still. So the idea is that if we take a system that looks like that, we can use vector arithmetic. To find the components. Right? So the idea is to find the components of B, find the components of A. Okay. So using this, you will get AX and AY, right? The X component of A and the Y component of A. And this one will give you the X, and this one will give you VY. Okay. So the idea is to use VX and use AX to find CX. And then we take VY and AY to find CY. And we do so by using the equation that you see located over here, right? So with A minus B is equal to C minus C, you end up having something that ends up looking like this. A plus B is equal to negative C. And that turns into AX plus VX is equal to negative CX, and then AY plus VY is equal to negative CY. So using those, you are capable of filling out the information in the table. You can find the table on the handout, and it's done during the experimental portion. So that's basically all you need to set up the experiment. So the idea is to fill out this table with the pertinent information that you need, right? A was 27 grams. So you write 27 here. It's at an angle of 63 degrees, so you write 63 here, and so on and so forth. Experimentally, the C that goes over here is the one that you observe here during the experiment. And the idea is to compare the C's that you get in table 1 with the calculated C's that you get from table 2, and then do a % error. And that concludes the theory portion of this video. In the experimental portion of this video, we're going to be using a force table that you see here, right? It's a table that goes from 0 all the way back to 0 for a total of 360 degrees, and it makes a circle, right? So the idea is that using a system of pulleys, right? You have one here, you have one there, and then you have one over here at different corresponding angles. Then we can find the mysterious third force given knowing the second and the first force. The force is basically the corresponding force that is caused by gravity. We're going to be hanging masses from this strand that you see passing through the pulley, with the idea of creating a system that is not in equilibrium, but as we move the third pulley around and change the corresponding mass hanging from it, eventually the system will go from non-equilibrium to equilibrium. When it becomes equilibrated, then this third one will be equal to the opposites of these two added, right? So if this is C and this is B and this is A, which you can see by the corresponding quadrant on the force table, you have an A. On this side, you have a B, and you have C for the third quadrant over here, right? Somewhere along this area is where the mysterious force should be positioned. So the idea is to follow the handout. The handout says to put a mass of 27 grams. So if we go to the scale, we have 27.1 is the mass for A. And then you position it in there, making sure, right, that the cord, you see the cord, should be on the pulley, right? So the angle that you're looking for on the pulley, right, can be determined by this indentation that you see in the pulley, right? It reads the third mark on the 60 for a total of 63 degrees, right? So this pulley on A is at an angle of 63 degrees and has a mass hanging from it of 27.1. Right? The handout says to use an angle of 154 for quadrant B. If you look at the indented line, right, this is 150, 151, 152, 153, and then the indentation there that you see is at 154. Right? So we're going to be hanging a total of 41 grams on that pulley. Right? So you take the 41 grams, you position them there, and now there we go. That's the corresponding setup for the experiment. So again, 27.1 grams at an angle of 63 degrees, 41 grams at an angle of 154 degrees, and now the mysterious pulley over here that has nothing hanging from it right now. And we can place a hanger in there. And the idea is that if you look at the ring in the middle, see how it's oriented towards the A and B quadrant? That's because there is nothing in C correspondingly, right? There's not enough weight and the angle isn't proper to make this balanced. So the force table, or rather the ring here on the middle of the force table, when it reaches equilibrium, will be in an equidistant position from all the quadrants, meaning it will look something like this. Right? So the goal of this experiment is to take the weight and the angle of C and then make it look like this. When I let it go, it goes there, right? So the first step should be to move the pulley a certain amount, right? With the idea that you can more or less try to balance just by looking more where it should be, right? So if you look here, the line coming out of C is kind of somewhere in between B and A. Right? So we leave it at that for now. It's currently at an angle of 298. Well, a little less than 298, but close enough. Right? So now the idea is that we're going to be adding masses. Right? So take masses, as you see here. Right? You add them, and then you see what happens. Right? Nothing much happened. Now we add another mass. Doesn't seem to make much difference, right? Another one. Then we add another mass, right? And now you see the system is starting to change, right? It's not in equilibrium, but at least now C has a fighting chance, right? So the idea is that you keep adding masses. In this case right now we're adding ones. So if you take a look, it's way more balanced now, right? Now if you look, the ring isn't touching the column in the middle, right? But that's still not quite right, right? So let's see if we can move the angle a little bit. And if I want you to see, right, I'm going to move it from its position over to 300, and then you can see how this changes the behavior, right? So it was initially at 297 over here, right? And I'm going to move it 298, 299, 300, 301. And so now if you look, the ring in the middle is balanced. Right? That means that at an angle of 301 degrees, you can see by the indentation, right? 301 degrees, and whatever the mass that I put in here, right? Take it out, you measure, you weigh it, and you get a mass of 49. That means that the system that balances the two forces A and B is a mass of 49 grams and an angle of 301 degrees. Okay. So, correspondingly, you go to your handout and then you write the corresponding values as appropriate. Right? You found 27.1 grams. You used 41.0 grams for B. The angle for A was 63 degrees. For B was 154 degrees. And now for C, you have 49 grams and an angle of 301 degrees. Right? So that fills out your experimental results. And then now the idea is to calculate what C should be, right? This is what we get experimentally. Experimentally, we got that we need a mass of 49 and a 301. Okay? So we write the values back down here that we got up there. That is going to be that. You can find the force by multiplying the mass in kilograms by the acceleration due to gravity, which is 9.8, right? So I'm only going to do A for you. 27 divided by 1,000 multiplied by 9.8. So that will be your force. Then the x component of the force will be 27 divided by 1,000 times 9.8 times cosine of the angle, which was 63 degrees. For the y component, 27 divided by 1,000 times 9.8 sine of 63 degrees. And you have the angle down here that you can put 63 degrees, 154 degrees, and 301 degrees. So the idea is to calculate what, oh sorry, that doesn't go there, right? The idea is to calculate what the mass of C should be based on this, and what the angle for C should be based on these, right? So, for example, let's say that when you do your calculations, you end up getting 49.3 grams. That's an example, right? So, 49.3 grams is what you should have gotten in the experiment, but what we got was 49. So the idea is to do a percent error on those numbers. 49.3 minus 49 versus what we should have gotten, 49.3 times 100, right? So that's basically how it would go. Right? Keep in mind, again, these numbers do not reflect the actual numbers that you should be getting, and they're just an example. Right? So the idea is that using the corresponding equations from the handout, right? A is square root of ax squared plus ay squared, and the angle can be found by the inverse tangent, and so on and so forth. You can find C by calculating A plus B, and that will give you the opposite of C. So using the calculations from the vector force table, you can calculate something that should be close to 49 and 301, and then do a percent error on that. The graphical sketches that you see here are basic representations of where the corresponding A, B, C, and all of them should look, right? So if you look at your diagram over there, right? If you base yourself on the 0 to the right, like a normal Cartesian axis, right? You have, only going to do A, right? That A should be pointing kind of like this, right? At an angle of 63 degrees, like so. So you can do that for vector V, for vector C, and then take all of those three combined and place them all in one single graphical sketch. And with that, you put that into your report, and that concludes the experiment. In this section, we're going to go through the process of doing the calculations needed to calculate the entries in table 2. The values that I'm going to be using are, again, just examples and are not indicative of what you saw during the experimental portion of this video. So now, if we use for vector A 10 grams and 30 degrees, and for vector B 20 grams and an angle of 150 degrees. Whatever C is can be determined based on your observations of the experiment. We'll make up values for that later once we find the analytical ones. So to do this, you need to take the values that you have here and populate table 2. So the mass for A is 10, the mass for B is 20, the angle for A is 30, and then 150, right? So those are the 4 entries that you got from table 1 that you put over in table 2. Now that you have this, we have to populate the rest of the table, and let's begin with the columns A and B. So the first entry is force, so we need to calculate force for A and B. Force in newtons can be found by calculating the mass in kilograms multiplied by the acceleration, which is in meters per second squared. In this case, because the hangers are hanging from the air, the acceleration that we use is the acceleration due to gravity, which is 9.8 meters per second squared. So with that in mind, we can find FA, right, the force for A, by using the mass. That's in grams, so you have to convert it to kilograms by dividing it by 1000. And then you multiply that by 9.8. This comes out to be 0.098 newtons. Then for FB, you do the same process, but this time with 20. And you get 0.196 newtons. With these numbers, you can now populate these entries over here. So 0.098 and 0.196. Now we move on to finding the x and y components. To find those, we need to use the equation that we have on the handout. FAX, right, the x component of force A, and then the y component of force A. So that is equal to force A cosine of the angle, and FAY is FA sine of the angle. So FA is 0.098, and then you multiply that by cosine of 30. And then FAY, the same, but with sine of 30. Doing the calculations for these, you get 0.085 newtons and 0.049 newtons. You do the same thing for B. the x, 0.196 times cosine of 150 gives you negative 0.170 newtons, and FBY gives you 0.196 sine of 150, which yields 0.098 newtons. Now that you have that, you can populate these entries that you have over here. So 0.085 and then 0.049. Here you have negative 0.170, and over here you have 0.098. With that, you have populated the entries for column A and column B. Now that you have that, we can go on and calculate the entries in column C. To do this, we need to use the equation on the handout. If you remember, it looks like this. The negative of vector C is equal to vector A plus vector B. In the handout, it appears as bold to symbolize that they are vectors. If you take this and then you break it into components, you get AX plus VX, and you get AY plus VY. So using the numbers that you have there, 0.085 minus 0.170, and for Y, 0.049 plus 0.098. Calculating these, you get negative 0.085 newtons and 0.147 newtons. Remember that this has negatives in there, so Cx is 0.085 newtons and Cy is equal to negative 0.147 newtons. Now you take that and you write these on your table, 0.085 and 0.147. Now we need to determine what the force for C is. We do that by finding the magnitude with this equation. So then square root of 0.085 squared plus negative 0. I forgot the negative over here. 147 squared. Calculating this, you get 0.170 newtons. So the force for this is 0.170 newtons. Now that you have found the force, you can go back to the original equation and solve for mass. So 0.170 newtons divided by 9.8 gives you a mass of 0.173 kilograms, right? Remember that the mass that you observe here is in kilograms. So the mass in grams is 17.3 grams. Just multiply that by 1000. So that means that what goes in here is 17.3 grams. Now to calculate the angle, you use the equation on the handout, inverse tangent of cy divided by cx. So using the numbers on the table, negative 0.147 divided by 0.085, like that, gives you an angle of negative 60 degrees. So now you need to determine where this is located, right? Because it says negative 60 degrees. To do this, you need to determine the nature of your c vector. And you do that by looking at cx and cy. Cx is positive and cy is negative. So if you go and you go to your Cartesian axis, positive, positive, negative, positive, negative, negative, positive, negative. So the fact that cx is positive and cy is negative means that you are located in the fourth quadrant, the one where x is positive and the y is negative. That means that the angle that you're looking for is relative to that position, because tangent of theta is opposite over adjacent. That means that the cy lies on the opposite side of the angle. So based on that, that means that if your vector is on the fourth quadrant and looks like this, then the angle that is negative 60 degrees has to be this theta, because when you run the opposite, and this is the adjacent. So in this case, the opposite is the y and the adjacent is the x. So that means that you're looking at it relative to the x-axis, meaning that if you take 360 and then subtract the 60, you get a total of 300 degrees. That means that for this problem, the angle for C is 300 degrees and the mass is 17.3. That means that when you were going through the experiment, you should have gotten something similar to that. So let's say that you did the hypothetical experiment and you got 17 grams. You got 17 grams and an angle of 298 degrees. So now that we have populated table 2, we can find the percent error. The percent error for the mass would be 17.3 minus 17 divided by 17.3, right? The calculations one is the one that is the correct one. And then multiply that by 100, and then you get your percent error. The percent error for the angle can be calculated the same way. 300 minus 298. The calculator says it's 300, so that's what you should have gotten, times 100. And that's how you calculate the percent error. And with that, that covers all the calculations for this experiment, and this concludes this video.